We talked about the dot product yesterday, so now let's have a look at some uses of it. What can we use it for? Finding the angle between two vectors, I guess, is the first application that we saw. And if we rearrange our dot product formula, we get this, that the cosine of the angle between the two vectors is u dot v over the magnitude of u times the magnitude of v. So if we have to find the angle between these two vectors, so cos theta will be u dot v, so we get -4 plus 3 over the magnitude of each of them. So root 1 squared, 2 squared, 3 squared, and root 4 squared, 2 squared, 1 squared. We end up with 3 on 7 root 6, which approximately, it's not an exact value, but it's going to be about 80 degrees to the nearest degree. Vector projections. So when we project one vector onto another one. Now, this was our formula. I think it's the easiest way of remembering the formula. U dot v over v dot v times v. But be careful. See, this question is not actually asking you for the projection, it's asking you for the length of the projection. So what that means is we need our projection, but we need to divide it by the magnitude. So u dot v over the magnitude of the projection is what we've got to find. 8 minus 10 minus 3 over root 2 squared, 2 squared, 1 squared, we get -5 over 3. Oh, actually, I probably should have put 5 over 3, shouldn't I? Because can the length be negative? So yeah, so I probably should have been 5 on 3, the answer for that one. Okay, but if we actually have to find the projection itself, okay, u dot v on v dot v times v. Basically, we're just plugging into that formula, 2 plus 3 minus 8 over, well, v dot v, remember, is the same as magnitude of v squared. So 1 squared plus 1 squared plus 2 squared. Multiply it by the vector we're projecting onto, and there it is. It's 3/4 times I plus j plus 2k. Perpendicular distance. Let's have a look at that. So we've got a point P, we want to find the perpendicular distance to this, line, vector, call it what you like, at mn. So mq, that's the projection of P onto the vector, what I've called n, so mn. I could also get mq by saying, well, that's vector mp plus the vector pq. It would get me the same vector. So playing around with that, I can come up with an expression for the vector PQ, and that's essentially what we're trying to find the length of, that vector, because that would be the perpendicular distance. So it would be MQ, which we said is the projection of P onto N, minus MP, which is the vector P. So if you like, there's a little formula we could use for the perpendicular distance. Let's use it to find the perpendicular distance of this point, 1, 0, 2, to the line joining B and C. Okay, so P, for the sake of my formula, I'm going to call that the vector BA, and U will be the vector BC, because essentially I'm going to be projecting BA onto BC. So we get, using the formula we've just worked out, a half of I minus j minus I minus 2j plus k. We want the magnitude of that particular vector, and that turns out to be root 22 on 2. Classify the triangle formed by these 3 points. You see, even though we're dealing with 3 dimensions, we can still have 2-dimensional shapes because it's just sitting on a particular plane in 3 dimensions. So what sort of triangle will we get when we join these 3 points up? I'm going to write each of the sides of these triangles as a vector. So there's AB, there's BC, and there's CA. So I'm like going around the triangle. I guess the first thing I looked at was, well, what's the length of the sides? That might tell me whether it's equilateral or isosceles or something like that. So the first one's root 14, second one root 12, third one root 2. Terrific. It's a scalene triangle. Fantastic. But then I noticed something else. 12 and 2 add up to 14. So this must satisfy Pythagoras' theorem. So we're talking about a right angle triangle because the length of CA squared plus the length of BC squared will give us AB squared. So we've got a right angle triangle. So that's because I approached it that way. Now, had I looked at it a little bit closer, I might have noticed that, hang on a sec, Look at BC and CA. When 0 is in the middle, and the numbers, well, -2 and -2, they're going to cancel out quite nicely. That dot product's going to be 0. Well, if that dot product's 0, I know those lines, or those vectors, are perpendicular to each other. So once again, we end up with the conclusion it's a right-angled triangle. It's a bit of a, you remember last year we looked at 3D trig, but now we can use vectors to solve these sort of problems. So A, B, C, D, base of a pyramid, side 2 units, V is the vertex. It's a symmetrical one, so it is a square pyramid where the vertex is directly over the centre of the base. Height of 4 units, we want to find, so it's the sort of question we saw in 3D trig, the acute angle between one of the slant edges and the base of the pyramid. So what I do is I sit my pyramid in our Cartesian space, but I place it sensibly. Because this is a symmetric one, I'm going to set it so that the vertex will be on the z-axis. So it'll set nice and symmetrically around. Now, because they've given me dimensions, I can come up with coordinates for all these vertices and play with that. The angle between one of the slant edges, it's all right, I'm going to use that slant edge. And the coordinates, they've told us the base is 2 units. And because I've got it sitting symmetrically, it must be 1 unit either side. So it must have coordinates 1, 1, and the z, of course, is 0 because it's the base. The vertex up the top then is 0, 0, and they told us it was a height of 4, so it's 4. So I can work out what that vector is. It would be -1, -1, 4, head minus tail. We have to find the angle between that and the base. So where do I draw the line to work out the angle? Well, I want it in the, like sitting in the plane. Therefore, I want to join it up to the origin here, because then I get that triangle sitting in a nice plane and I can work out the angle that it makes with the base. That vector I can work out, it's joined up to the origin. Notice where I've placed the head, because when we're finding the angle between 2 vectors, you work the angle out at the tail, where the 2 tails are. So that'll be -1, -1, 0. So now I'll put it into our dot product formula. Cos theta u dot on magnitude u magnitude v. Cos theta is 1/3, so 71 degrees. If you do get a question like this, the implication of the question is that you're going to use vector methods. Otherwise, what's the point of asking it in an extension 2 paper? So don't bring it back to 3D trig and just use 3D trig and do all that. It's not what they're expecting, and quite possibly won't get you the marks. Okay. In fact, they might even say using vector methods or something like that. The medians of a triangle meet at a point. Prove that the medians divide each other in the ratio 2 to 1. Here's a triangle. I suppose this question could have just as easily been asked in extension 1, because it doesn't really matter whether I'm dealing with 2 dimensions or 3 dimensions. I'm just talking about a flat shape. So here's my triangle. I'll give the sides there. I'll call OA the vector A, OB the vector B, it makes sense. Now I want the midpoint because we're talking about the medians. So X is going to be my midpoint of OA. So it's a half of A as far as the vector goes. And then I can do the same on OB. So that would be a half of B. A median, if you recall, is the line that joins the midpoint to the opposite vertex. So let's draw those 2 medians in. They meet at Z, and we want to prove they divide each other in the ratio 2 to 1. Okay. Let's give OZ a name. So we'll call that the vector Z. Seems to make sense. Now Z is going to divide BX in a certain ratio. Let's call it M to N. And hopefully it'll end up being 2 to 1. That's what we're trying to prove. So the ratio of the vector AZ over ZY would be M over N. Playing around with that, I get N lots of AZ is M lots of ZY. Those vectors, head minus tail. So I get Z minus A for the first one, B over 2 minus Z for the second one. And just moving things around a bit, I come up with M plus NZ equals NA plus MB over 2. But you see, Z also will divide AY in the ratio M to N. So in other words, I could say that these ratios are equal. We know that. I mean, that's a feature of a triangle. The medians cut each other in the same ratio. We're just trying to find out what that ratio is. So we'll just manipulate this little equation. Remember, we're trying to work out what the ratio of m to n is. But because we've now ended up, look at these two vectors. They're both b minus a. So they'll cancel. And I get the ratio m on n is 2 on 1. That's what we were looking for. Excellent. So we know they divide each other in the ratio 2 to 1. Application of the dot product. Where do I use the dot product? I just realised that. I did not use the dot product there. Oh, well, it was a nice question anyway. Okay, it was a great one to finish off with, wasn't it? Applications of the dot product. There you go.